We now look at the second example, which is a ballistic pendulum. Ballistics deals with the speeds of bullets and projectiles, and the ballistic pendulum has been used historically to measure the speed of bullets. Now we can measure those by high-speed cameras, but these cameras were not available in the past, so they used the ballistic pendulum to do this. So it's two strings with a block of wood over here, and here we have, for example, our gun, which is going to fire the bullet, and the bullet goes and it enters the block of wood and it lodges somewhere inside. And so it's a perfectly inelastic collision that one object goes and hits another one, and then because of the momentum of the bullet, the whole thing is going to swing upwards and it's going to go, let's say, up to here. Okay, it will swing to a certain height. So if this is the y-axis, this is y equal to 0 or initial, and it will swing to this y final position. Now we consider the mass of the bullet is mb, and the mass of the block of wood, this is the block of wood, it's going to be m capital B. The speed of the bullet is u1, and as it enters it, the whole thing is going to swing upwards with a velocity v of the block. Well, it's going to be block plus bullet, and then it's going to swing upwards, and at this point the velocity of the block is going to be 0. So that we'll say is our v final. Okay, and that is 0. Now this is what we are trying to find. So this is a two-step problem. In the first step, the bullet enters the block. This is a perfectly inelastic collision, and then the block swings upwards, and the kinetic energy of the block will convert into the potential energy of the block plus bullet. So the kinetic energy converts into potential energy, and the kinetic energy came from its motion, which was due to the conservation of momentum here. So in the first step, it's a perfectly inelastic collision. Inelastic collision. And we have the conservation of momentum. Sum of p x initial is sum of p x final. So the initial momentum is going to be the mass of the bullet, u of the bullet, plus mass of the block, and the u of the block is 0, and because it's lodged inside, so we'll have mb plus m capital B. That's the mass of the two together times the speed with which they are both moving off. Now this is our objective, so we can say that the speed of the bullet is going to be mass of the bullet plus mass of the block over mass of the bullet times VB. So if we can find VB, we will get UB because we know the masses of the bullet and the block. So here we now go to the conservation of kinetic energy. Well, not the conservation, but the conversion of kinetic energy into potential energy. And we can say that the delta K plus delta UG is equal to external force and friction. There's no external force, there's no friction, so it's 0. Now delta K will be K final minus K initial, and this will be UG final minus UG initial. K final is going to be half, and the mass is going to be the bullet plus the block. V final, that's the position up here, the initial is going to be this position here as soon as it starts leaving. So it's going to be half mass of the bullet, mass of the block, times VB, which we want to find and put in here, plus the UG final is going to be mass of the bullet plus mass of the block times G times Y final minus UG initial is going to be mass of the bullet plus mass of the block G Y initial, they add up to 0. Now there's no effect of the horizontal motion on the potential energy. It only depends on the Y motion or the displacement in the Y direction. So there's no X component here. Now V final, we know right here is going to be 0. So we can cancel that out. We can always consider Y initial to be 0. So we can cancel this out. Now Y final is going to be this height by which it has gone up, and we can call that Y final, or it's also written sometimes as the height which it gains. So we can replace that with the height. Now in this equation, these two terms are gone. We have only these two terms, and MB plus MB is common to both. We can cancel that out. So on this side we'll have minus half VB, and we can bring that on the other side, so it's minus GY final, or H. The negatives will cancel, and VB is going to be 2GH. There's something wrong here. That's a square and a square. So there's a square. Sorry about that, but that fixes this, so it's a square. And this means that VB is the square root of 2GH. So once we get the VB, once we get the H, we get the VB, and we plug in the VB here to get the UB. How do we get the H? Well, this moves up and down, and there are devices which can note its highest position. When it swings down, it will just note how high it went. We can get that not with much difficulty, and so we can measure the velocity of the bullet. Now we come to collisions in 2 dimensions. So this will be 2D collisions, and first one we'll take is a easier one, which is a perfectly inelastic collision, in which the two objects will stick together. And the case that we'll take is the same as what we have in the textbook. So we have a car which is labeled as 1, moving with a velocity u1 in the I direction. So that's our x and y, so that's in the I direction. And another vehicle, that's number 2, that's moving with the speed, initial speed of u2 in the j direction, so that becomes its velocity. They have a collision here, and they both move off at some angle, but they go off together, so they're sort of crushed and stuck together, and they move off in this direction at some velocity v at some angle theta. And the question is, what is v and what is theta? So because we have 2 objects and the result is one object moving together, so it's a perfectly inelastic collision. And now instead of breaking up into x and y components, we'll do it in a vector form, just to have another way of doing it. And we will say that the sum of the momenta initial is the sum of the momenta final, and I'll write these as vectors instead of x and y components. Well, they will become x and y components, but writing that as a vector. So the initial momentum is going to be the momentum of this object plus this object. So it's going to be m1 u1 plus m2 u2, going to be m1 plus m2 v, and the v is the vector of that. Now m1 u1 will be m1 u1, well, its value is u1 I, and this will be m2 u2 j, that's m1 plus m2, and it's going to be vxi plus vyj. This v will have two components, the x component and the y component. The x component is vx and the y component is vy. So v is going to be vxi plus vyj. Now, the I can only be equal to the I and the j can only be equal to the j. So if we separate out the i's, we'll get m1 u1 equals m1 plus m2 vx, and the j equation will give us, that's the I equation, the j equation will give us m2 u2 is going to be m1 plus m2 vy. Now if we know u1 and u2, so we know u1, u2, and we know the masses, so in this equation everything is known except vx. So from here we get vx, and from here we get vy, and then the magnitude of the final velocity is vx squared plus vy square root, and the theta, this angle at which it goes, is tangent inverse vy over vx, and we get the theta. Or we can simply write that v is vxi plus vyj. So that's how we can get this, the direction and velocity. Now, in practice, if you have a collision, you don't know the initial velocities, but by looking at the tire marks on the ground, you can find the angle, and the police do that. They measure this angle, so they know that this was the resulting angle, and by the length of the tracks, they can get an idea of the velocity. So if you know these two, you can go back and calculate how fast they were going. Okay, so this example is also solved in the book along with some numbers. Now let's take the last case, which is two-dimensional collision, but in an elastic collision. Elastic collisions, molecules collide with each other. They are perfectly elastic. So we will consider the collision of two particles. Could be two atoms or two molecules or two protons. So let's assume that you have object number 1 moving to the right with the velocity u1, and to keep it simple, the other object is here a little bit lower than that, so it's not a head-on collision, but it's what we call a glancing collision. And in a glancing collision, the object u1, or number 1, will go off at some angle, and 2 will go off at some other angle. It's not going to bounce backwards, and it's not a head-on collision, but it's going to go forwards. So that's the initial condition. And as it hits it, let's assume that we can draw it from here, that object number 1 is going off with at a velocity v1. Now it's a vector, it will have x and y components, and object 2 is going off with a velocity v2. And this will also be a vector, it will have x and y components. And let's say that this is angle theta and this is angle phi. So now we write the momentum conservation equation and the kinetic energy conservation equation because it's elastic. So from the momentum conservation equation, let's say the momentum conservation in the x direction would give us, these two are the initial conditions and these two are the final conditions. So it's going to be m1, mass of this one, u1 purely in the x direction, plus 0 equals m1. Now this is going in this direction at angle theta, so it will have an x component v1x, which is going to be v1 cos theta, and it will have a v1y, which is v1 sine theta. So the x component is going to be m1 v1 cos theta, and then this one is going to have an x component v2x, which is v2 cos phi, and a y component which is v2y, which is v2 sine phi. So in the x direction we'll have this one and we'll have this one. So it's going to be plus m2 v2 cos phi. Okay, so it's mass times its velocity in the x direction. So that's one equation. In the y direction, there's no component here, no component here, so it's going to be 0 plus 0. And here we have this component, so it's going to be m1 v1 sine theta, and this is in the negative y. Okay, so that's our x and y. So this is the negative y, so it's minus m2 v2 sine phi. So that's our first equation, that's our second equation. And now we go to the kinetic energy equation. So the initial kinetic energy of these two is half m1 u1 square plus 0, because this was stationary, and it's going to be half m1 v2 square, m1 v1 square for this one, plus half m2 v2 square, that's this magnitude of this velocity squared times this mass. Okay, so we have these three equations, and if we count the unknowns, we have we'll have to assume that we know the initial velocity and we know the masses. So the unknowns are going to be v1, this speed, and v2, and theta and phi, and the knowns are m1, m2, and that's it, u1, these three, and u2, which we took as 0. So now we have three equations and we have four unknowns, and with three equations and four unknowns, it's impossible to solve this equation. Well, it can be solved, but we can solve it. We can get an infinite number of solutions. So we don't get a unique solution. So we need four equations to solve for four unknowns. So one way is that if we measure theta in this collision, well, then we can get all the other things. Or if we measure phi, or we measure v1, or we measure v2, at least one of these must be known. Now, a reason why we can't solve it is, if you look at this figure closely, so here's our m2, that's the center line, and m1 is not on the center line, but it's moving here. So m1 is going to hit m2 somewhere here, and it's going to bounce off in this direction. But if it's a little bit higher, it's going to hit it here, and it's going to bounce off at a smaller angle. Or if it's a little bit lower, it's going to hit it here, it's going to bounce off at some other angle. And we are not given this information. If we were, yeah, we could possibly find theta and solve it. But we don't know this thing, and therefore that's the reason why we can't solve it. So we must have at least one of these. Now, there is one special case, that if m1 equals m2, so if these two are like two protons or two deuterons or an oxygen atom hitting another oxygen atom, if the masses are equal, then we find that the angle theta plus the angle phi added together will always become 90 degrees. So in other words, if the two were of equal mass, then this total angle would be 90 degrees. And this provides us with the fourth equation. And now for equal mass objects, we can solve this equation and get the final answer, because wherever it hits, if you get an angle theta of some value here, we will know this angle because these two must add up to 90 degrees. So it really reduces one of the unknown because we have one more equation. Okay, so this is these are the 4 cases that we wanted to do, and now we'll look at the center of mass in the next video.